There's a star you can observe with a decent backyard telescope that according to our measurements is older than the universe itself. This isn't science fiction or clickbait, this is HD 140283, nicknamed Methuselah after the biblical figure who supposedly lived 969 years, and it represents one of the most fascinating puzzles in modern cosmology. The star sits just 190 light-years away in the constellation Libra, close enough that we can study it in remarkable detail, yet distant enough in time that it carries secrets from the universe's infancy. When astronomers first calculated its age using multiple independent methods, they arrived at a figure around 14.4 billion years, give or take 800 million years. The problem? The universe itself is only 13.8 billion years old. Something here doesn't add up, and that something tells us extraordinary things about the early cosmos, the formation of the first stars, and the limits of our measurements. Let's start with what we know for certain. HD 140283 is what astronomers call a subgiant star, meaning it has exhausted the hydrogen fuel in its core and begun the process of expanding into a red giant, though it hasn't quite gotten there yet. This evolutionary stage is actually helpful for age determination because we understand the physics of stellar evolution incredibly well. Stars are like cosmic clocks, burning through their fuel at rates determined by their mass and composition, and by examining a star's properties we can reverse engineer its age with remarkable precision. HD 140283 has about 80 to 90% the mass of our Sun, but here's where things get interesting: it contains almost no elements heavier than helium. In astronomical terminology, these heavy elements are called metals, even though we're talking about things like carbon, oxygen, and iron. The star's metallicity is less than 1% of the Sun's, making it what we call a population II star, formed from nearly pristine material that existed shortly after the Big Bang. The early universe was chemically simple in a way that's hard to overstate. After the Big Bang, the cosmos consisted almost entirely of hydrogen and helium with trace amounts of lithium. That's it. Every other element on the periodic table, from the carbon in your cells to the iron in your blood to the gold in jewelry, had to be manufactured inside stars through nuclear fusion and then scattered into space through stellar winds and supernova explosions. The first generation of stars, called population III stars, were massive monsters made of nothing but primordial hydrogen and helium. We've never actually observed one of these stellar titans directly because they burned out billions of years ago, living fast and dying young in spectacular supernovae that seeded the cosmos with the first heavy elements. HD 140283 represents the second generation, population II stars that formed from gas clouds slightly enriched by the death of those first stars, but still incredibly metal-poor compared to younger stars like our Sun. The age calculation for HD 140283 relies on several techniques that cross-check each other beautifully when everything works correctly. The primary method uses stellar evolution models that track how stars change over time. We measure the star's brightness, temperature, and chemical composition, then run computer simulations that model the nuclear reactions in its core, the convection of material through its interior, and the radiation escaping from its surface. These models predict how quickly a star of a given mass and composition will evolve through different life stages. By matching HD 140283's observed properties to these evolutionary tracks, astronomers can pinpoint where it sits on its life timeline. Additionally, we use astroseismology, the study of stellar oscillations, to probe the star's internal structure. Stars ring like bells with frequencies that depend on their internal composition and density, and by analyzing these vibrations we can determine properties that would otherwise remain hidden beneath the surface. The metallicity measurements add another crucial constraint. We use spectroscopy to analyze the light from HD 140283. Identifying absorption lines created when different elements absorb specific wavelengths of light as it passes through the star's atmosphere. The strength and pattern of these lines tell us not just which elements are present but in what quantities. The extreme metal poverty of HD 140283 immediately signals that it formed very early in cosmic history, before many generations of stars had enriched the interstellar medium with heavy elements. When we feed this chemical composition into our stellar models, they consistently point toward an age exceeding 14 billion years, with the most refined calculations placing it around 14.46 billion years with an uncertainty of plus or minus 800 million years. Now here's where the cosmic bookkeeping gets uncomfortable. Multiple independent lines of evidence tell us the universe is 13.797 billion years old with an uncertainty of only about 20 million years. This figure comes from the Planck satellite's exquisitely detailed measurements of the cosmic microwave background, the afterglow of the Big Bang that fills all of space. The CMB carries imprinted patterns from tiny density fluctuations in the early universe, and by analyzing these patterns we can determine cosmological parameters with incredible precision. The Hubble constant measurements, which track how fast the universe is expanding, provide another age estimate that agrees remarkably well. Observations of the oldest globular clusters, dense spherical collections of ancient stars, also support this timeline. When you have three completely different methodologies converging on the same answer, you can be pretty confident in the result. So we're left with an apparent paradox where our best measurement of the universe's age is 13.8 billion years, and our best measurement of this particular star's age is 14.4 billion years, with uncertainty ranges that barely overlap. The naive interpretation would be that we found a star older than the universe, which would be like finding a person older than their parents, a logical impossibility that would require us to throw out fundamental physics. But before we start rewriting cosmology, we need to examine where uncertainties might be hiding in our measurements. The error bars on HD 140283's age are substantial, roughly 800 million years in either direction. This uncertainty comes from several sources that compound when you're trying to measure something as complex as a star's age. First, there's the distance measurement. Even though 190 light-years is cosmically nearby, determining the exact distance to a star remains challenging. Parallax measurements from satellites like Gaia have dramatically improved our distance estimates, but small errors in distance translate into larger errors in luminosity, which then propagate through the age calculation. If the star is slightly closer than we think, it's intrinsically dimmer, which might make it younger. If it's farther, it's brighter and potentially older. Chemical composition introduces another layer of uncertainty. While we can measure the overall metallicity quite accurately, the relative abundances of different elements matter too. The ratio of carbon to iron, the presence of alpha elements like oxygen and magnesium, and even the helium abundance all influence how a star evolves. Some of these elements are harder to measure precisely, especially helium, which leaves few spectral lines in a star's visible spectrum. Our stellar evolution models make assumptions about the initial helium abundance based on Big Bang nucleosynthesis calculations, but if the real value differs even slightly, the derived age changes accordingly. The physics inside stellar models contains uncertainties as well. We understand the basic nuclear reactions that power stars extremely well, but details like the efficiency of convection, the treatment of diffusion where heavy elements gradually sink toward the core, and the precise opacity of stellar material at different temperatures all involve approximations. These aren't wild guesses, they're based on laboratory measurements and theoretical calculations, but they're not perfect either. A small change in how we model convective mixing could shift the age estimate by hundreds of millions of years. When astronomers published their most recent refined age estimate for HD 140283 in 2013, they explicitly addressed the apparent conflict with the universe's age. By carefully accounting for all sources of uncertainty and using improved distance measurements from Hipparcos satellite data, they arrived at 14.46 plus or minus 0.8 billion years. The key word here is plus or minus. That 800 million year uncertainty range means the star's true age could be as low as 13.66 billion years or as high as 15.26 billion years. The lower end of this range fits comfortably within the universe's age, while the upper end would indeed present a serious problem. Statistically speaking, given the uncertainties involved, there's no actual conflict, just a measurement that pushes tantalizingly close to the cosmic age limit. Think of it this way: if you measured someone's height as 6 feet with an uncertainty of plus or minus 6 inches, and separately measured a doorway as 6 feet 2 inches tall, you wouldn't immediately conclude the person can't fit through the door. You'd recognize that within the measurement uncertainties, the person might be 5'6" or 6'6", and the doorway might be slightly taller or shorter than measured. The same logic applies here. The measurements are consistent within their error bars, which means we don't yet have a genuine paradox that requires new physics to resolve, though we do have a fascinating constraint that pushes our measurements to their limits. What makes HD 140283 scientifically valuable isn't the apparent age conflict, it's what the star tells us about the early universe. This star formed when the cosmos was still in its infancy, probably within the first few 100 million years after the Big Bang. At that time, the universe looked dramatically different from today. Galaxies were just beginning to coalesce from the cosmic web of dark matter and gas. The first generation of massive stars had exploded, but there hadn't been many generations of stellar recycling yet. The interstellar medium contained only trace amounts of heavy elements, barely enough to form planets or complex chemistry. Population 2 stars like HD 140283 give us a window into this primordial epoch. By studying their chemical compositions in detail, we can work backward to understand what the first supernovae were like. Different types of supernovae produce different patterns of elements. Quark-collapse supernovae from massive stars create lots of alpha elements like oxygen, magnesium, and silicon. Type Ia supernovae from exploding white dwarfs produce more iron peak elements. The specific ratios of elements we measure in HD 140283 tell us about the mix of stellar deaths that enriched the gas cloud from which it formed. This is cosmic archaeology, reading the chemical fingerprints left by stars that died billions of years before our solar system even existed. The star's motion through the galaxy provides additional clues to its origin. HD 140283 is moving extremely fast relative to the local stellar neighborhood, traveling at about 400 kilometers per second. This high velocity suggests it doesn't belong to the Milky Way's disk where most stars orbit relatively sedately. Instead, it's probably a member of the galactic halo, a roughly spherical distribution of old stars that surrounds the disk. The halo represents the ancient building blocks of our galaxy, stars that formed early and have been orbiting through the Milky Way for billions of years. Some halo stars might even be remnants of smaller galaxies that merged with the Milky Way in the distant past. HD 140283's trajectory and composition mark it as a survivor from this ancient population, a stellar fossil that has witnessed the entire history of galaxy formation. Let's zoom out and consider what we know about the earliest stars in the universe. Theoretical models suggest that the very first stars, those population 3 monsters made of pure hydrogen and helium, were extraordinarily massive, perhaps 100 to 300 times the mass of the Sun. Without any heavy elements to help cool the collapsing gas clouds that formed them, these clouds couldn't fragment into smaller pieces the way modern star-forming regions do. Instead, they collapsed into single massive objects. These stellar behemoths would have burned incredibly hot and bright, fusing hydrogen into helium in their cores at prodigious rates. Their lifetimes would have been cosmically brief, just a few million years from birth to explosive death. When these first stars died, they didn't go quietly. The most massive ones would have exploded as pair-instability supernovae, catastrophic detonations so energetic they completely obliterate the star, leaving no remnant behind. These explosions released tremendous amounts of energy and scattered the first heavy elements into space. The lighter stars in this first generation might have collapsed directly into black holes without exploding, locking their material away forever. Either way, we don't expect any population 3 stars to still exist today. They all died billions of years ago, living fast and dying young like cosmic mayflies. But their deaths seeded the universe with the ingredients needed for the next generation. Even a tiny amount of carbon, oxygen, or iron in a gas cloud dramatically changes how it can cool and collapse. Heavy elements act like thermostats, absorbing energy and radiating it away more efficiently than pure hydrogen and helium can. This means that gas clouds enriched even slightly with metals can fragment into smaller pieces, forming stars with a wider range of masses, including long-lived low-mass stars that can survive for many billions of years. HD 140283 represents this second generation, formed from gas that was perhaps 99.9% hydrogen and helium but contained just enough heavy elements to fundamentally alter the star formation process. The search for truly pristine population 3 stars continues to motivate astronomers. Finding even one would be an extraordinary discovery, offering a direct look at the universe's first stars rather than the indirect evidence we have now. The challenge is that these stars would be incredibly distant, since we'd need to look back to when the universe was only a few 100 million years old. Even our most powerful telescopes struggle to detect individual stars at such vast distances. The James Webb Space Telescope, with its infrared vision and unprecedented sensitivity, gives us perhaps our best chance yet to spot the signature of these primordial giants, either by detecting them directly or by observing the galaxies they inhabited. Some researchers think we might find population 3 stars closer to home than expected. In rare cases, a small cloud of primordial gas might have remained isolated from the rest of the universe, sheltered from the metal enrichment that spread through most of the cosmos. If such a cloud collapsed to form stars much later, those stars would have population 3 characteristics despite forming billions of years after the first generation. These local population 3 stars would be invaluable laboratories for studying pristine stellar physics without needing to peer across billions of light years. So far, despite extensive searches, no confirmed examples have been found, but the hunt continues. HD 140283's location just 190 light-years away makes it accessible to detailed study in ways that more distant ancient stars are not. We can measure its properties with high precision, track its motion through space accurately, and monitor it for subtle variations that might reveal additional secrets. Some astronomers have used it as a test case for new measurement techniques, treating it as a sort of cosmic calibration standard. If we can perfect our age dating methods on HD 140283, where we have the luxury of detailed observations, we can apply those same techniques to more distant and poorly studied ancient stars with greater confidence. The broader context of cosmic age measurements reveals why precision matters so much. Understanding the universe's age connects to almost every aspect of cosmology. It tells us about the expansion rate of the universe through the Hubble constant. It constrains the density of dark matter and dark energy, the mysterious components that dominate the cosmic energy budget. It determines the timeline for structure formation, telling us when the first galaxies, stars, and black holes could have appeared. An uncertainty of even a few 100 million years in the cosmic age translates into significant uncertainties in all these connected measurements. The cosmic microwave background provides our most precise cosmic clock. This radiation, released when the universe was only 380,000 years old, carries an incredibly detailed imprint of conditions at that early time. The temperature fluctuations in the CMB span a range of angular scales, from tiny spots to broad regions covering large areas of the sky. These patterns encode information about the composition and geometry of the universe. By fitting theoretical models to the observed pattern, we can extract values for cosmological parameters including the age of the universe, the Hubble constant, the density of ordinary matter, dark matter, and dark energy, and the geometry of space itself. The Planck satellite mapped the CMB with exquisite detail from 2009 to 2013, producing what is likely to remain the definitive measurement for many years. The resulting age estimate of 13.797 billion years comes with an uncertainty of just plus or minus 0.023 billion years, or about 23 million years. This remarkable precision emerges from analyzing hundreds of thousands of temperature measurements across the entire sky and fitting them to sophisticated theoretical models. The level of agreement between theory and observation in the CMB data is stunning, with the standard cosmological model fitting the data almost perfectly across many decades of angular scale. But there's a wrinkle in this beautiful picture, one that makes the HD 140283 age measurement even more intriguing in context. This is the Hubble tension, a growing discrepancy between different methods of measuring the universe's expansion rate. When we derive the Hubble constant from the CMB, assuming the standard cosmological model, we get about 67 km per second per megaparsec. But when we measure it using local distance ladder methods, building up from nearby stars to more distant galaxies, we get about 73 km per second per megaparsec. These measurements disagree by roughly 9%, which might not sound like much, but the uncertainties on each measurement have shrunk to the point where they no longer overlap. Both methods have been checked and rechecked, both appear robust, yet they give incompatible answers. The Hubble tension might indicate new physics beyond the standard cosmological model. Perhaps dark energy evolves over time rather than remaining constant. Maybe there are additional relativistic particles we haven't accounted for. Some exotic proposals involve modifications to gravity or interactions between dark matter and dark energy. Alternatively, there might be subtle systematic errors in one or both measurement methods that we haven't identified yet. Resolving this tension stands as one of the major challenges in cosmology today, and age measurements of ancient stars like HD 140283 provide an independent constraint that could help break the deadlock. Here's why ancient stellar ages matter for the Hubble tension. If the local measurements are correct and the Hubble constant is truly around 73, then the universe is younger than the CMB suggests, perhaps closer to 12.5 to 13 billion years. If the CMB measurements are correct at 67, the age is indeed about 13.8 billion years. Stars like HD 140283 give us a completely independent age estimate that doesn't rely on either the CMB or the distance ladder. If we could nail down the ages of multiple ancient stars with precision better than the current uncertainties, we'd have a third method to weigh in on which expansion rate is correct. Unfortunately, stellar age determinations haven't yet reached the precision needed to definitively resolve the tension, but they provide a valuable sanity check. The technique of using stellar ages as cosmic chronometers has a long history. Globular clusters, dense spherical collections containing hundreds of thousands to millions of stars, have served as key age indicators for decades. These clusters all formed at roughly the same time from the same gas cloud. So all their stars have the same age and chemical composition but different masses. By plotting their stars on a color magnitude diagram, astronomers can identify the turnoff point where stars are just beginning to exhaust their core hydrogen and evolve off the main sequence. The position of this turnoff point directly indicates the cluster's age, since more massive stars evolve faster and reach the turnoff sooner. The oldest globular clusters in the Milky Way have ages around 12 to 13 billion years based on this turnoff method, comfortably younger than the universe itself. These ages used to have uncertainties of 1 billion years or more, but improvements in distance measurements, stellar evolution models, and our understanding of chemical composition have gradually tightened the constraints. Modern estimates for the oldest globular clusters converge on ages around 12.5 to 13 billion years, suggesting they formed within the first billion years after the Big Bang. This timeline fits well with our understanding of galaxy formation, where the first globular clusters appeared early as some of the first bound stellar systems. Individual stars like HD 140283 complement globular cluster studies by providing different constraints. In a cluster, you average over hundreds of thousands of stars, which smooths out individual variations but limits how precisely you can measure any single star. With an isolated field star, you can focus all your observational resources on that one object, potentially achieving higher precision on its individual properties. The trade-off is that you don't have the benefit of knowing that hundreds of thousands of other stars have the same age, so your systematic uncertainties might be larger. Using both approaches gives a more complete picture. One fascinating aspect of HD 140283 is that despite its age and metal-poor composition, it shows no signs of having planets. Many astronomers have searched for planetary companions around ancient stars, wondering whether planet formation could occur in the metal-poor environment of the early universe. The leading theory of planet formation, core accretion, requires significant amounts of heavy elements to build up the rocky and icy cores that become planets. In a gas cloud that's 99.9% hydrogen and helium, there isn't much solid material available for planet building. This suggests that the universe's first stars probably didn't have planetary systems, at least not rocky planets like Earth. However, recent exoplanet discoveries have challenged this assumption. A few planets have been found orbiting stars with metallicities even lower than HD 140283, though these are extremely rare. One possibility is that these planets formed through an alternative mechanism, perhaps by gravitational instability where dense regions in a protoplanetary disk collapse directly into planets without needing a solid core first. Another intriguing idea is that some material from previous generations of stars accumulated in particular regions of space, creating pockets with higher heavy element abundances even in an overall metal-poor environment. Planets forming in these pockets would have more raw materials to work with. The absence of detected planets around HD 140283 doesn't definitively prove none exist. Our planet detection methods have biases toward finding large planets close to their stars or planets that happen to transit across the stellar disk from our viewing angle. A small rocky planet in a wide orbit might easily escape detection even with our current techniques. As technology improves and we conduct longer-term monitoring of nearby stars, we might yet discover that some ancient stars harbor hidden planetary systems. Finding planets around population 2 stars would revolutionize our understanding of where and when planets can form. Let's consider what the sky would look like from a hypothetical planet orbiting HD 140283, even though none probably exist. The stellar sky would be dramatically different from Earth's night sky because this star belongs to the galactic halo, far above the plane where most stars concentrate. Looking up, you'd see fewer stars than from Earth, with the Milky Way band appearing dimmer and possibly at an odd angle depending on the planet's orbital orientation. The constellations we know wouldn't exist because you'd be seeing everything from a different vantage point. Our sun would be utterly invisible, a dim speck lost among billions of other stars if you could even find it at all. But here's the mind-bending part. If an observer had existed on such a planet throughout HD 140,283's lifetime, they would have witnessed essentially the entire history of the visible universe unfold around them. In the early eons, they would have seen a cosmos dominated by hydrogen and helium, with the first galaxies just beginning to light up the darkness. Over billions of years, they would have watched galaxies merge and evolve, new stars forming from progressively more metal-rich material. They would have seen the Milky Way assemble from smaller protogalactic fragments. If we imagine this observer possessing impossibly advanced technology, they could have watched our Sun form 4.6 billion years ago, seen the Earth coalesce from the protoplanetary disk, witnessed the rise of life and its evolution through mass extinctions and radiations, all from their perch orbiting an ancient star. This thought experiment highlights just how different the timescales of stellar and cosmic evolution can be. Stars like HD 140283, with masses slightly less than the Sun, burn their fuel conservatively enough to survive for many billions of years. More massive stars flash through their lives in cosmic instants, some living only a few million years before exploding. The most extreme cases are the most massive stars known, which can exhaust their fuel in just a few 100,000 years, rushing from birth to death on timescales shorter than it took for modern humans to evolve. Meanwhile, the smallest red dwarf stars, with masses around 10% of the Sun, burn so slowly that the universe isn't yet old enough for any of them to have died. The smallest red dwarfs could theoretically shine for 1 trillion years, outliving not just HD 140283 but the entire current era of star formation in the universe. The chemical composition of HD 140283 tells us that several generations of massive stars must have lived and died before it formed, even though it's one of the oldest stars we can observe. The presence of any heavy elements at all, even in trace amounts, proves that earlier stars enriched the gas. We can estimate how many stellar generations this might require using chemical evolution models that track how supernovae release different elements. The rough answer is that it probably took somewhere between 3 and 10 generations of massive star formation, each lasting just a few million years, to produce the chemical pattern we observe in HD 140283. This means even this ancient star, formed within the first 500 million years of the universe, represents the product of a complex evolutionary sequence. The oxygen-to-iron ratio in HD 140283 is particularly informative. Oxygen comes primarily from core-collapse supernovae, the explosions of massive stars, while iron is produced in larger quantities by type Ia supernovae, the thermonuclear explosions of white dwarfs. The relative abundances of these elements tell us about the balance between these two supernova types in the early universe. HD 140283 shows an oxygen-to-iron ratio much higher than the Sun's, suggesting it formed in an environment where core-collapse supernovae dominated and type Ia supernovae hadn't yet had time to significantly contribute. This makes sense because type Ia supernovae require an aging stellar population to produce white dwarfs first, a process that takes at least 1 billion years or so. Other elements provide additional puzzle pieces. The abundances of carbon and nitrogen constrain the contribution from asymptotic giant branch stars, evolved intermediate mass stars that dredge up fusion products to their surfaces and blow them into space through stellar winds. The presence of elements like strontium, barium, and europium indicates contributions from neutron capture processes, either the slow S process occurring in aging stars or the rapid R process in neutron star mergers and rare types of supernovae. Each element carries information about specific nucleosynthesis sites, and together they paint a picture of the early universe's chemical landscape. Modern stellar spectroscopy allows us to measure abundances for dozens of elements in bright stars like HD 140283. High-resolution spectrographs can detect absorption lines from incredibly rare elements, some with abundances millions of times lower than hydrogen. This level of detail transforms stars into archaeological sites, preserving records of long-dead stars in their chemical makeup. It's analogous to how geologists read Earth's history in rock strata, except we're reading cosmic history in stellar atmospheres, with each element representing a different chapter of the early universe's story. The study of metal-poor stars has become its own subdiscipline within astronomy, with dedicated surveys searching for the most pristine stars we can find. Projects like the Hamburg/ESO survey, the Pristine Survey, and searches using data from the Gaia satellite have identified thousands of candidate metal-poor stars. Spectroscopic follow-up then measures their detailed compositions. Among these, a few ultrametal-poor stars have been found with iron abundances less than 1/10,000th of the Sun's. These stars might be only one generation removed from the truly pristine population 3 stars, formed from gas clouds touched by just 1 or 2 early supernovae. One famous example is SMSSJ 031300.36-670839.3, a star with less than 1/10,000,000th of the Sun's iron abundance. This star has detectable carbon but almost no iron, suggesting it formed from material enriched by a special type of supernova called a faint supernova, where most of the iron fell back into the compact remnant rather than being ejected into space. Stars like this give us glimpses of individual stellar deaths in the early universe, with each chemical signature potentially representing a single supernova explosion rather than the averaged contribution of many stars. They're like forensic evidence from specific ancient events, allowing us to reconstruct what happened star by star rather than just seeing the statistical average. HD 140283, while not as metal-poor as these extreme examples, remains important precisely because it's bright enough and close enough for incredibly detailed study. We can measure its chemical composition to high precision, track its motion through space accurately, and even attempt astroseismology to probe its interior structure. This makes it a benchmark against which we can calibrate our understanding of ancient stellar populations. If we can perfect our techniques on HD 140283, we can then apply them to more distant or fainter ancient stars with greater confidence. The astroseismology of HD 140283 deserves special attention because it provides constraints unavailable through other methods. Stars oscillate with periods ranging from minutes to hours, pulsating in complex patterns as sound waves bounce around inside them. These oscillations create tiny variations in the star's brightness and in the wavelengths of its spectral lines. By measuring these variations precisely, we can determine the internal sound speed, which depends on temperature and composition. Different oscillation modes penetrate to different depths, allowing us to effectively conduct seismology of the stellar interior just as we study Earth's interior using earthquake waves. For HD 140283, astroseismic observations have helped constrain its mass and evolutionary state more precisely than would be possible from surface observations alone. The frequency pattern of oscillations is sensitive to the star's core density and the boundary between the helium core and hydrogen envelope. As a subgiant star, HD 140283 has already exhausted the hydrogen in its core and begun to evolve toward the red giant phase. The position along this evolutionary track determines the age, and astroseismology provides additional constraints that narrow the range of possible ages. This technique has become increasingly powerful with dedicated space missions like Corot and Kepler that monitored thousands of stars continuously, though HD 140283 is bright enough to study from the ground as well. The future of ancient star studies looks promising as new facilities come online. The James Webb Space Telescope can push observations to unprecedented distances and sensitivities, potentially detecting individual ancient stars in galaxies billions of light-years away. The extremely large telescope, currently under construction in Chile with a primary mirror 39 meters across, will have the light-collecting power to perform detailed spectroscopy on much fainter ancient stars than currently accessible. The Nancy Grace Roman Space Telescope will conduct wide-field surveys that could identify many more nearby ancient stars like HD 140283. Each new generation of instruments opens possibilities that were science fiction just decades earlier. Ground-based surveys using automated telescopes and sophisticated data processing pipelines have already revolutionized the search for rare objects. Projects like the Sloan Digital Sky Survey and its successors have photographed hundreds of millions of stars and galaxies, creating datasets so large that traditional methods of manual analysis are impossible. Instead, machine learning algorithms scan through the data, identifying candidates for detailed follow-up. A human astronomer might have spent a career discovering a handful of metal-poor stars in the pre-digital era. Modern surveys find thousands, enabling statistical studies that reveal population-wide patterns invisible when looking at individual objects. The Gaia satellite, mentioned earlier for its distance measurements, deserves special recognition for transforming our understanding of the Milky Way. Launched in 2013, Gaia has measured positions and motions for nearly 2 billion stars with unprecedented accuracy. These measurements reveal the galaxy's structure and history in ways never before possible. By tracking how stars move, we can run the clock backward, determining where different stellar populations originated. This has revealed that the Milky Way cannibalized numerous smaller galaxies throughout its history, with streams of stars from these disrupted galaxies still visible in Gaia's data. HD 140283's motion suggests it might be a remnant from one of these early merger events, though determining exactly which one remains challenging. The concept of galactic archaeology has emerged from these studies, treating the Milky Way as an archaeological site where different layers correspond to different epochs of galaxy formation. Just as archaeologists excavate through strata to reveal human history, galactic archaeologists study stellar populations to reveal galactic history. The oldest stars, those from the halo like HD 140283, represent the deepest and earliest layer. The thick disk, a population of moderately old stars, formed during a period of intense star formation perhaps triggered by early mergers. The thin disk where the Sun resides contains younger stars formed more recently in a relatively stable environment. Each population carries information about the conditions when it formed. Chemical tagging takes this further by using detailed chemical compositions as fingerprints. Stars formed in the same molecular cloud should have nearly identical chemical patterns because they all condensed from the same well-mixed material. By identifying groups of stars with matching chemical signatures, even if they're now scattered across the galaxy, we can identify stars born together and thus reconstruct the history of star formation. In principle, we might even be able to find siblings of the Sun, other stars that formed in the same molecular cloud 4.6 billion years ago but have since dispersed throughout the galactic neighborhood. None have been definitively identified yet, but the search continues. HD 140283's chemical signature might similarly help identify other stars from the same ancient star-forming event, though the search becomes difficult given how old the star is and how much time stellar orbits have had to mix different populations together. If we could find a cluster of stars with nearly identical compositions, all about as old as HD 140283, we might be able to determine whether it formed in a globular cluster that subsequently dissolved. In a dwarf galaxy that merged with the Milky Way, or in the protogalactic environment of the Milky Way itself. Each scenario would tell us something different about early galaxy assembly. Thinking about the Milky Way's assembly history raises fascinating questions about where our galaxy came from. Cosmological simulations show that galaxies like the Milky Way grew through a combination of smooth gas accretion and violent mergers with smaller galaxies. The precise balance between these processes determines the galaxy's final structure. Too many major mergers would have destroyed the disk, creating an elliptical galaxy instead. Too few would have left the galaxy as a small, quiescent system without much star formation. The Milky Way's structure suggests a history of numerous minor mergers and a few moderately significant ones, but nothing so violent as to completely disrupt the galactic disk. The largest merger in the Milky Way's recent past was probably the Gaia-Sausagen-Celadus event, where a dwarf galaxy containing perhaps 10 to 100 billion stars worth of material plowed into the Milky Way about 8 to 10 billion years ago. This collision deposited a significant population of stars into the halo and thick disk, including many metal-poor ancient stars. Some astronomers have speculated that HD 140283 might be a relic from this merger, though its extreme age makes this uncertain. The timing would require the dwarf galaxy itself to have formed very early and then spent several billion years orbiting independently before merging with the Milky Way. Even more ancient mergers must have occurred when the universe was much younger. The Milky Way's oldest globular clusters probably formed before the main body of the galaxy assembled, meaning they might represent the cores of even smaller protogalactic fragments that merged to build the Milky Way. Reconstructing this deep history requires finding the oldest possible stars and determining their origins through chemistry and kinematics. It's detective work on a galactic scale, piecing together clues scattered across billions of years. The question of what conditions were actually like in the early universe brings us back to the cosmic microwave background and the physics of the first few 100,000 years. After the Big Bang, the universe was an opaque plasma where photons constantly scattered off free electrons. As the universe expanded and cooled, it eventually reached a temperature where electrons and protons could combine into neutral hydrogen atoms, an event called recombination. Without free electrons to scatter off, photons could suddenly travel freely through space, creating the cosmic microwave background we observe today. This happened when the universe was 380,000 years old. Before recombination, the universe was essentially featureless to electromagnetic observations. No stars existed yet, no galaxies, just a hot, smooth plasma gradually cooling as space expanded. This period is called the Cosmic Dark Ages, dark not because it was actually dark but because we can't see into it using light. The CMB marks the boundary of the observable universe in the electromagnetic spectrum. To probe earlier times, we would need different messengers like gravitational waves or neutrinos that can pass through the opaque early plasma. The first stars probably formed somewhere between 100 and 200 million years after the Big Bang, ending the Dark Ages and beginning the epoch of reionization. These first stars were so luminous that their ultraviolet radiation ionized the hydrogen gas around them, creating bubbles of ionized plasma that gradually expanded and merged. By the time the universe was about 1 billion years old, essentially all the hydrogen in the universe had been reionized. We can study this transition by observing very distant quasars whose light has traveled through the intergalactic medium, but many details remain uncertain. HD 140283 formed during or shortly after this epoch of reionization, in an environment radically different from the modern universe. The intergalactic medium was hotter, denser, and chemically simpler. Galaxies were smaller and more irregular, frequently merging and interacting. Star formation rates were higher on average, with some galaxies forming stars hundreds of times faster than the Milky Way does today. Black holes and galactic centers were still growing toward the supermassive sizes we observe in mature galaxies. The universe was a more chaotic and energetic place. Imagining what a molecular cloud collapsing to form stars looked like in this environment requires combining many pieces of physics. Without significant heavy elements, the gas couldn't cool as efficiently, meaning the characteristic mass scale for fragmentation was different. Simulations suggest that population 2 star formation might have produced a different mass distribution than modern star formation, possibly with a bias towards somewhat more massive stars on average. HD 140,283's mass around 0.8 to 0.9 solar masses might represent the lower end of what commonly formed, with very low mass stars being rarer in the early universe. The subsequent evolution of HD 140283 over its 14 billion year lifetime would have been mostly uneventful. For the vast majority of this time, the star sat on the main sequence, steadily fusing hydrogen into helium in its core through the proton-proton chain reaction. This is the same basic process that powers the Sun, though HD 140283 burns slightly slower due to its lower mass and different composition. The star would have appeared slightly cooler and redder than the Sun, with a surface temperature around 5,700 Kelvin compared to the Sun's 5,800 Kelvin. Over billions of years, the helium gradually accumulated in the core while the hydrogen envelope remained largely unaffected. The core slowly contracted and heated up as helium ash piled up, increasing the rate of hydrogen fusion in a shell around the core. This caused the star's luminosity to gradually increase, a process that occurs in all main sequence stars. Our Sun has brightened by about 30% over its 4.6 billion year lifetime and will continue to brighten. HD 140283 has experienced even more dramatic changes given its much longer lifetime. About 1 billion years ago, give or take, HD 140283 exhausted the hydrogen in its core and began to transition off the main sequence. The core, now pure helium, couldn't generate energy through fusion because the temperature wasn't yet high enough to ignite helium burning. Instead, the core contracted under gravity while hydrogen fusion continued in a shell around it. This shell burning produced energy that pushed the outer envelope outward, causing the star to expand and cool, beginning its evolution toward red giant status. HD 140283 currently sits in the subgiant phase of this evolution, larger and more luminous than when it was on the main sequence but not yet bloated into a full red giant. Eventually, perhaps within the next billion years, the core will become hot enough and dense enough to ignite helium fusion through the triple alpha process, where 3 helium nuclei combine to form carbon. This helium ignition will stabilize the star temporarily on what's called the horizontal branch, where it will burn helium in the core and hydrogen in a shell for perhaps 100 million years. After exhausting core helium, the star will ascend the asymptotic giant branch, becoming a large, luminous red giant that pulses and loses mass through a stellar wind. Eventually, HD 140283 will shed its outer envelope entirely, creating a planetary nebula and leaving behind a white dwarf remnant. That white dwarf, a dense ember about the size of Earth containing roughly half the star's original mass, will then cool slowly over trillions of years, fading from white-hot to yellow to red to eventually becoming a black dwarf, a dark cinder barely warmer than the cosmic microwave background. But the universe isn't old enough yet for any black dwarfs to exist. Even the oldest white dwarfs, formed from the first generation of stars to complete their life cycles, are still glowing feebly in the ultraviolet and visible spectrum. HD 140283's remnant will join this population of ancient white dwarfs, carrying its chemical legacy into the far future. The white dwarfs from ancient stars provide yet another cosmic chronometer. White dwarfs cool at a predictable rate determined by their mass and composition. Much like stellar evolution follows predictable tracks. By measuring a white dwarf's temperature and composition, we can estimate how long it has been cooling, which tells us when the progenitor star died. The coolest, faintest white dwarfs are necessarily the oldest, formed from stars that died billions of years ago. Surveys searching for these ancient white dwarfs in the Milky Way have found populations with cooling ages approaching 12 billion years, again supporting the picture of a universe roughly 13.8 billion years old with the oldest stars forming within the first billion years. One particularly interesting aspect of white dwarf studies is that they can help constrain exotic physics. White dwarfs are supported against gravity by electron degeneracy pressure, a quantum mechanical effect where electrons cannot occupy the same quantum state. This creates a pressure independent of temperature that can support the star even as it cools to near absolute zero. The cooling rate depends on how heat escapes from the interior, which in turn depends on the opacity of the white dwarf material. If exotic particles like axions exist and are produced in the hot interior, they could carry away additional energy, causing the white dwarf to cool faster than standard theory predicts. Careful measurements of white dwarf cooling ages thus constrain theories beyond the standard model of particle physics. HD 140283's eventual white dwarf remnant will contain the products of all the nuclear burning that occurred during its lifetime. The core will be mostly carbon and oxygen from helium burning, with perhaps some neon from late-stage burning if the star reaches high enough temperatures. The outer layers might retain some helium from the hydrogen burning shell. This chemical structure will be locked in place as the white dwarf cools, creating a stratified object that preserves a record of the star's fusion history. Astronomers studying white dwarfs billions of years from now could analyze HD 140,283's remnant and deduce its history, just as we study ancient white dwarfs today to learn about stars that died long ago. This brings us to a profound realization about the nature of stellar archaeology. Every star we observe is a time capsule containing information about the epoch when it formed. The chemical composition tells us what the interstellar medium was like. The kinematics reveal the dynamical state of the galaxy. The age constrains the cosmic timeline. But unlike archaeological artifacts on Earth, which we can physically excavate and examine in laboratories, stars remain distant beacons that we can only observe from afar. We cannot touch them, cannot sample them directly, can only analyze the light they send across the cosmos. This makes spectroscopy absolutely essential. When we split starlight into its component wavelengths, we're conducting a form of remote chemistry, identifying elements and even isotopes across light-years of space. The absorption lines in a stellar spectrum act like fingerprints, each element producing a characteristic pattern of lines at specific wavelengths determined by quantum mechanics. By matching observed patterns to laboratory measurements, we can determine not just which elements are present but their abundances, their ionization states, their velocities, even their isotopic ratios in some cases. It's a remarkable feat that this works at all, that quantum mechanics operates identically across billions of light-years, allowing us to interpret distant starlight. The technology of spectroscopy has advanced enormously since the pioneering work of Fraunhofer, Kirchhoff, and others in the 19th century. Modern spectrographs can achieve spectral resolutions exceeding 100,000, meaning they can distinguish wavelengths that differ by 1 part in 100,000. At this resolution, we can measure Doppler shifts from stellar motion with precision better than a meter per second, about walking speed. We can detect isotopic shifts, the tiny wavelength differences caused by atoms of different masses vibrating at slightly different frequencies. We can see spectral lines split by magnetic fields through the Zeeman effect, revealing the strength and structure of stellar magnetism. HD 140283 has been observed with many of these advanced techniques over the years. High-resolution spectroscopy has measured abundances for dozens of elements. Precise radial velocity measurements have confirmed it's not in a binary system, which would complicate age determinations. Studies of its chromospheric activity, the magnetic heating of its outer atmosphere, have provided additional constraints on its rotation and age, since stellar rotation slows over time due to magnetic braking. All these observations fit together to create a comprehensive picture of this ancient star. One detail that emerges from careful study is that HD 140283 shows some degree of chemical peculiarity compared to other metal-poor stars. It has an unusually high carbon abundance for its metallicity, making it technically a carbon-enhanced metal-poor star, though the enhancement is modest compared to more extreme examples. This carbon enrichment might indicate contamination from a binary companion that went through the asymptotic giant branch phase, dredging up carbon from helium burning and transferring it to HD 140283 through a stellar wind or mass transfer. However, no companion has been detected, so if this scenario occurred, the companion would now be a very faint white dwarf. Alternative explanations for the carbon enhancement include inhomogeneous mixing of supernova ejecta in the early universe, where HD 140283 formed from a gas cloud that happened to receive more material from carbon-rich supernovae. Or it might indicate that some of the first generation of stars had unusual properties, perhaps including significant rotation that affected their nucleosynthesis. Each possible explanation has implications for our understanding of early stellar evolution and chemical enrichment, making HD 140,283's peculiar composition scientifically interesting beyond just its age. The broader population of metal-poor stars shows diverse chemical patterns that tell a complex story. Some stars are enhanced in elements produced by the R process, the rapid neutron capture process that occurs in neutron star mergers and possibly rare types of supernovae. These stars might have formed from material enriched by just one or two neutron star merger events, inheriting dramatically enhanced abundances of elements like europium, uranium, and thorium. The radioactive decay of uranium and thorium can actually be used for additional age dating, a sort of nucleocosmochronology, though the uncertainties are typically larger than stellar evolution ages. Other metal-poor stars show patterns suggesting enrichment by parainstability supernovae, the extraordinarily energetic explosions of very massive first-generation stars. These explosions produce distinctive abundance patterns with high ratios of odd-numbered elements to even-numbered ones and unusual amounts of zinc relative to iron. Finding stars with these signatures provides evidence that parainstability supernovae really occurred in the early universe, confirming theoretical predictions. Each newly discovered ancient star potentially represents a different channel of chemical enrichment, a different piece of the puzzle of how the first stars lived and died. The pristine survey mentioned earlier takes a clever approach to finding metal-poor stars efficiently. Rather than obtaining expensive high-resolution spectroscopy for millions of stars to measure their metallicities directly, the survey uses a narrowband filter centered on the calcium H and K absorption lines. The strength of these lines provides a good first estimate of metallicity that can be measured with relatively simple and inexpensive observations. The survey then prioritizes the most metal-poor candidates for detailed spectroscopic follow-up. This strategy has proven extremely effective, identifying hundreds of stars with iron abundances below 1,000th of the Sun's. Some of these discoveries have been particularly exciting. The star SPLUS J2104-0049 has an iron abundance only 1/10,000th of solar but is enhanced in carbon and other elements, suggesting it formed from material enriched by just one or two massive first-generation stars. Its chemical pattern is so unusual that it constrains the masses and explosion mechanisms of the first stars more tightly than population-averaged studies can. Another star, 2-mass J18020002-510438, appears to have inherited material from a very massive star that underwent a faint supernova, ejecting carbon and other light elements but retaining most of its iron. Each of these ancient stars is like a witness to a specific early event, a single supernova or stellar death that we can study through the chemical fingerprints left behind. Looking at the bigger picture, the concordance between different cosmic age measurements is actually quite remarkable. The CMB gives 13.8 billion years. The oldest globular clusters give 12.5 to 13 billion years, allowing time for them to form after the Big Bang. The coolest white dwarfs give cooling ages approaching 12 billion years, consistent with the oldest stars dying and leaving remnants. Radioactive dating of the oldest meteorites in our solar system gives 4.567 billion years for the formation of the solar system, fitting comfortably within the cosmic timeline. Even geological evidence from Earth, including the oldest known rocks and minerals at about 4 billion years, fits the picture. Everything hangs together consistently. This consistency wasn't always the case. In the mid-20th century, there was a famous controversy where the measured expansion rate of the universe implied an age younger than the ages of the oldest stars, an obvious impossibility. The resolution came from realizing that the distance measurements to galaxies were wrong due to confusion between different types of variable stars used as standard candles. Once this systematic error was corrected, the cosmic age increased to a value comfortably older than the stellar ages. The current Hubble tension might represent a similar situation where subtle systematic errors are creating an apparent conflict, or it might indicate genuine new physics. Time and better measurements will tell. The fact that HD 140,283's age uncertainty overlaps with the cosmic age, even if the central values differ, illustrates both how far we've come and how much room remains for improvement. We can measure the age of a star 190 light-years away to within 800 million years, an uncertainty of about 6%. We can measure the age of the universe to within 23 million years, an uncertainty of about 0.2%. These are extraordinary achievements, but they're not yet precise enough to resolve every question. Future improvements in distance measurements from Gaia, better stellar evolution models incorporating improved physics and chemical compositions, and possibly even astroseismic observations from future space missions could tighten HD 140,283's age uncertainty to perhaps 500 million years or even better. Similarly, future CMB experiments and other cosmological probes could refine the cosmic age further, though we're approaching fundamental limits set by cosmic variance, the random fluctuations intrinsic to the initial conditions of the universe. At some point, the uncertainty in the age of the universe will be limited not by measurement precision but by the fact that the universe's properties were set by quantum fluctuations that are inherently probabilistic. We're not at that limit yet, but we're closer than we've ever been. The philosophical implications of studying objects like HD 140283 deserve consideration. This star has existed for nearly the entire history of the universe, witnessing cosmic evolution from the chaotic early eons through the gradual settling into the more ordered state we observe today. If we could somehow access this star's complete history, we would have a record spanning from shortly after the Big Bang to the present day, a chronicle of 14 billion years of cosmic change. Of course, stars don't keep records in any conventional sense, but their chemical compositions and internal structures encode information about their formation and evolution that we can extract through careful study. This makes ancient stars like HD 140283 precious beyond their individual scientific value. They're irreplaceable windows into epochs that are otherwise extremely difficult to observe. The first billion years of cosmic history remain poorly understood in many ways, and every ancient star we can study in detail helps fill in the picture. As these stars age and eventually die, we lose direct probes of the early universe. Although their white dwarf remnants will persist, extracting detailed chemical information from a cool, dense white dwarf is much harder than from a bright giant or subgiant star like HD 140283 currently is. This creates a sort of urgency in the study of ancient stars. While HD 140283 itself will likely survive for another billion years or so before entering advanced stages of stellar evolution, other ancient stars are nearing the ends of their lives right now. Some might explode as supernovae within the next few million years if they're massive enough. Others might already be shedding their envelopes as planetary nebulae. Each one that dies represents a lost opportunity to study primordial material in detail. This motivates comprehensive surveys to find and characterize as many ancient stars as possible while they're still accessible. The connection between HD 140283 and broader questions in cosmology and astrophysics illustrates how different areas of astronomy interweave. You can't fully understand this one star without considering stellar evolution theory, galactic dynamics, chemical enrichment, cosmological age determinations, and the history of structure formation in the universe. Each discipline informs the others, creating a web of interconnected knowledge. This holistic nature of astronomical research is part of what makes it so fascinating, as discoveries in one area often have implications for seemingly unrelated questions. For instance, precise measurements of stellar ages directly impact our understanding of dark matter. The formation of the first stars depended on how quickly dark matter could clump under gravity to create the potential wells where gas could collect and collapse. The timing and distribution of early star formation thus constrains dark matter properties like its temperature, whether it's cold, warm, or hot. Finding very ancient stars in unusual locations might indicate that dark matter behaves differently than our standard models assume, though no definitive evidence for such deviations has been found in HD 140283 or other ancient stars studied so far. The study of HD 140283 also connects to questions about the formation and evolution of the Milky Way itself. Our galaxy grew through a complex process involving both smooth accretion and mergers, and the old stellar population preserves a record of this history. By mapping the positions, velocities, and chemical compositions of thousands of ancient stars, astronomers are reconstructing the Milky Way's family tree, identifying which stars came from which progenitor galaxies. HD 140283 represents one data point in this massive undertaking, but an important one given how well we can characterize it. The future of HD 140283 observations might include some surprising possibilities. As our technology advances, we might eventually be able to detect planets around a star even if they're small and in wide orbits. We might measure neutrinos or gravitational waves from fusion reactions in its core, though this would require detectors far more sensitive than anything currently available. We might use it as a gravitational lens to study more distant objects if a background star happens to pass almost directly behind it from our viewing angle. Each new observational technique opens possibilities that were inconceivable when the star was first studied. One particularly exciting prospect is that future space-based observatories might allow direct imaging of HD 140283's surface. Current interferometric techniques can barely resolve the disks of the largest nearby stars, but future observatories combining light from multiple telescopes separated by hundreds or thousands of meters could achieve angular resolutions fine enough to see details on stellar surfaces. If we could image HD 140283's surface directly, we might be able to detect star spots, measure differential rotation between the equator and poles, observe convection cells, or see chemical inhomogeneities. This would provide tests of stellar atmosphere models that are currently impossible. The broader context of ancient star studies points toward an exciting future for the field. New surveys will find more extreme examples, stars even more metal-poor than HD 140283, perhaps even discovering the first genuine population 3-star or at least a star enriched by only a single prior supernova. The James Webb Space Telescope is already searching for evidence of the first stars by looking for specific signatures in the spectra of distant galaxies. Next-generation extremely large telescopes will push these studies further. The coming decades promise major advances in our understanding of the earliest epochs of cosmic history. At the same time, HD 140283 reminds us of the importance of nearby objects that we can study in exquisite detail. While searching for the most distant galaxies or the most extreme objects captures headlines, there's enormous value in thoroughly characterizing well-studied nearby objects. HD 140283 has been observed hundreds of times over the decades, with each new generation of instruments revealing additional details. This iterative process of observation, modeling, and refinement is how astronomy progresses. The star serves as a benchmark, a calibration target, and a test case for new techniques. The story of HD 140283, the star that appeared older than the universe, ultimately illustrates both the power and limitations of astronomical measurements. We can determine the age of a distant star to within several hundred million years, an extraordinary feat considering we're analyzing light that has traveled across nearly 200 light-years of space. Yet this precision isn't quite enough to completely eliminate the apparent paradox, leaving room for continued refinement. The resolution, that the uncertainty ranges overlap even if the central values seem uncomfortably close, demonstrates the importance of properly accounting for errors and not overinterpreting marginal discrepancies. More broadly, HD 140283 represents a triumph of astrophysics. We understand stellar structure and evolution well enough to look at a point of light in the sky and determine with reasonable confidence that it has been shining for over 14 billion years. We understand nuclear physics well enough to know what reactions power the star and how they've evolved over its lifetime. We understand cosmology well enough to measure the age of the universe to a precision of better than 1%. We understand chemistry well enough to read the abundance patterns in the star's atmosphere and deduce what early supernovae must have been like. All of these pieces fit together into a coherent picture of cosmic history from the Big Bang to the present. Yet for all we know, mysteries remain. We don't fully understand how the first stars formed or exactly what they were like. We don't know all the details of how galaxies assembled or how supermassive black holes grew so quickly. We can't yet explain the Hubble tension or definitively identify dark matter. Questions about the ultimate fate of the universe, whether it will expand forever or eventually recollapse, remain open despite major progress. HD 140283 helps constrain some of these questions while raising others, as any good scientific observation should. In the end, this ancient star sitting in our cosmic backyard serves as a reminder of how much history surrounds us if we only know how to read it. The light reaching our telescopes tonight left HD 140283 around the year 1835, during the Industrial Revolution, when Darwin was beginning to formulate his theory of evolution and the nature of stars remained mysterious. That light carries information about a star that was already billions of years old when Earth formed, a star that witnessed the assembly of galaxies, the formation of heavy elements through countless stellar deaths, the gradual enrichment of the cosmos that made planets and life possible. By studying this light, we connect to deep cosmic history, reading messages written in spectral lines that span the history of the universe. That HD 140283 exists at all, a survivor from the ancient universe still shining brightly enough for detailed study, is itself remarkable. That we can analyze it well enough to determine its age to within a billion years, well, that's nothing short of extraordinary.